Transmission towers, also known as power transmission towers, power towers, or electricity pylons, play a crucial role in supporting overhead power lines. These tall structures, typically constructed of steel lattice, carry high-voltage transmission lines that transport electricity from generating stations to substations. The substations then distribute power to end users through distribution lines supported by utility poles, which carry low-voltage conductors. Designing transmission towers is a critical engineering task that involves civil, mechanical, and electrical engineering concepts. These towers must support heavy conductors at a safe height above the ground and withstand various natural calamities. To minimize transmission losses, voltage is increased stepped up after power generation for long-distance transmission. At the receiving end, the voltage is decreased stepped down for use by electrical loads. Transmission lines at various voltage levels 132 kV, 220 kV, 400 kV, 765 kV are employed throughout the power system network to transmit bulk power effectively. As a result, transmission towers must ensure minimum ground clearance according to the system voltage. Transmission lines serve as crucial links between generating stations and distribution systems, and with the rapid growth in developing countries, an increase in the number of transmission towers has been observed. These towers stretch from generating station switchyards to substations located near populated areas, supporting the high-voltage conductors of overhead power lines. The shape, height, and sturdiness of transmission towers depend on the stresses they encounter. Although these towers do not conduct electricity themselves, they provide a pathway for lightning discharges to reach the ground through a ground wire strung along the top of the structure. Transmission tower conductors are typically made from steel-reinforced aluminum cable ACSR aluminum conductor steel-reinforced and are generally arranged in sets of 3 for 3-phase alternating current AC transmission. Occasionally, a fourth neutral cable is used for short-distance transmission, but this is not common. Conductors are grouped by phase, with 1 conductor line per group 3 total, 2 conductor lines per group 6 total, or more. These groups are installed in multiples of 3 e.g., 3, 6, 9 and may be arranged in a triangular shape or parallel to each other. Three-way grouping enhances transmission efficiency. At the top of a transmission tower, 1 or 2 smaller, solitary wires, known as overhead ground wires, static wires, or pilot wires, can be observed. These wires serve the purpose of absorbing or deflecting lightning strikes, safely conducting electricity to the ground. Under normal conditions, the voltage potential of these wires is 0, meaning they do not carry electricity. Some overhead ground wires are integrated with fiber optic cables that transmit telecommunication data. Fiber optic cables, made of glass, do not conduct electricity and are unaffected by lightning strikes. Additionally, fiber optic cables running a few feet below the transmission conductors may be observed. Adding telecommunication lines increases the return on investment for building transmission networks. These fiber optic lines may be operated by the utility company or leased to cable or phone companies. An EHT extra high-tension transmission tower is comprised of several key components: the peak of the tower, the cross arm that holds the transmission conductor, the cage of the transmission tower, the transmission tower body, the leg of the transmission tower, and the stub anchor bolt and baseplate assembly located at the base of the tower. Transmission towers need to support heavy conductors at a safe height above the ground and endure various natural calamities. Designing these towers is a vital engineering task that incorporates civil, mechanical, and electrical engineering principles. When designing a transmission tower, it is essential to consider the following aspects: minimum ground clearance to ensure that the lowest points of the conductors are safely above ground level, insulator string length to determine the correct length for the insulator strings, clearances to maintain the minimum required clearance between conductors and between conductors and the tower, ground wire location to properly position the ground wire in relation to the outermost conductors, and midspan clearance to consider the dynamic behavior of the conductors and the need for effective lightning protection. Transmission tower design considerations: when designing transmission towers, several key aspects must be taken into account: minimum permissible ground clearance H1, maximum sag of the overhead conductor H2, vertical spacing between the top and bottom conductors H3, vertical clearance between the ground wire and top conductor H4. Higher voltage transmission lines require greater ground clearance and vertical spacing. High voltage towers, therefore, necessitate higher ground clearance and larger vertical spacing between conductors. The following factors should be considered when selecting a transmission tower. Height of the tower ensures adequate clearance. Base width of the tower impacts stability. Length of the cross arm determines conductor spacing. Single circuit or double circuit tower, depending on the transmission requirements. Voltage kV capacity, different voltage levels necessitate specific designs. Angle of deviation affects tower design and placement. Soil type, wind speed, and zone, environmental factors that influence tower stability. Length of the insulator assembly ensures proper insulation. Minimum clearances between ground conductors and the tower. Location of the ground wire relative to the outermost conductor. Midspan clearance addresses the dynamic behavior of conductors and lightning protection. Minimum clearance above ground level for the lowest conductor. Crossing considerations for power lines, railway lines, roads, and rivers. Material and current types. Transmission towers can be classified based on the material used and the current types. When it comes to materials, these are steel structure, wooden material, RCC reinforced cement concrete pole. When it comes to current types, HVAC high voltage alternating current transmission towers, HVDC high voltage direct current transmission towers. Railway traction line tower. Voltage capacity classification. Transmission towers are also categorized based on their current carrying capacity in kV, 11 kV, 33 kV, 66 kV, 110 kV, 132 kV, 220 kV, 400 kV, 500 kV, 765 kV, 800 kV, 1000 kV, 1100 kV, 1200 kV. This classification aids in selecting the appropriate transmission tower based on specific requirements and conditions of the transmission line. Transmission tower types. Transmission towers can be grouped into several types with many variations. Common types include suspension towers. Conductors are suspended between towers using suspension insulators. Terminal towers. Conductors connect to a substation or underground cable via strain insulators. Tension towers, designed to handle cable weight and axial loading. Transposition towers, change the position of conductors relative to each other. Structure configuration and material. The structure cost typically constitutes 30 to 40% of the total cost of a transmission line. A structure study determines the most suitable configuration and material based on cost, construction, maintenance, and electric and magnetic field effects. Key factors include horizontal phase configuration, generally the most cost-effective. Vertical configuration may be more efficient if right-of-way costs are high or if space is restricted. Right-of-way and tree clearing, horizontal configurations require more space. Electric and magnetic field strength, vertical configurations generally have lower field strengths at the right-of-way edges. Selection of structure type and material, selection depends on design loads. For a single-circuit 230 kV line, cost estimates for single-pole and H-frame structures in wood, steel, and concrete are considered. Wood H-frames have the lowest installed cost with a 1,000-foot design span. Transmission tower design. Transmission tower designs include lattice steel towers LST, a steel framework with bolted or welded components. Tubular steel poles TSP, hollow steel poles fabricated as single or multiple pieces. Key specifications for tower design. Specifications include voltage, number of circuits, type of conductors and insulators, future circuit additions, transmission line tracing, tower site selection, and conductor configuration. Typical tower heights range from 15 to 55 meters 49 to 180 feet. Additional considerations include variations in permissible ground clearance based on voltage level, sag determined using a sag template, vertical spacing between conductors, and vertical clearance between the earth wire and the top conductor. These factors ensure effective lightning protection and compliance with load limitations.